Welcome students to this lecture of the unit Chemical Bonding and Molecular Structure. In this lecture we will discuss the following topics: valence shell electron pair repulsion theory and its applications, concept of hybridization and its types, structure of various inorganic molecules on the basis of hybridization and valence shell electron pair repulsion theory, resonance and resonating structures. First, let us discuss the introduction to the topic. Lewis' concept is unable to explain shapes of molecules. Sidgwick and Powell in 1940 put forth valence shell electron pair repulsion theory to explain shapes of molecules. The theory was later improved by Gillespie and Nyholm in 1957. The main points of this theory are: the shape of molecule depends upon the number of valence shell electron pairs bonding as well as non-bonding around the central atom. The valence shell electron pairs repel each other since they are negatively charged. The electron pairs tend to occupy such positions in space that minimize repulsion and thus maximize distance between them. The multiple bond is treated as if it is a single electron pair, and the electron pairs of a multiple bond are treated as a single super electron pair. The repulsive forces of electron pairs decreases in the order lone pair, followed by lone pair, followed by bond pair repulsions. Nyholm and Gillespie explained that the lone pairs of electrons in a molecule occupy more space and they are localized on central atom, and bonding electron pairs occupy less space as these are shared between two atoms. Thus, lone pair of electrons cause much repulsion than bond pairs. If the central atom of molecules is linked to similar atoms and contains only bonding electron pairs, all repulsions are equal. The shape of molecule is symmetrical and the molecule is said to have a regular geometry. If a central atom is linked to different atoms or is surrounded by bonding as well as lone pairs of electrons, the repulsions between them are different. As a result, the molecule has an irregular or distorted geometry. Now, let us discuss the common shapes of molecules. There are various shapes that are commonly found in various molecules. In the images shown, the yellow groups are non-bonding electron pairs, the white groups are bonded atoms, and the pink is the central atom. Linear, trigonal planar, bent, tetrahedral, trigonal bipyramidal, T-shaped, octahedral, square pyramidal, seesaw, and square planar. Now, let us discuss the concept of hybridization. Hybridization may be defined as the phenomena of intermixing of atomic orbitals of slightly different energies of the atom by redistributing their energies to form new set of orbitals of equivalent energy and shape. During hybridization, the atomic orbitals with different characteristics are mixed with each other. Hence, there is no meaning of hybridization between same type of orbitals. That is, mixing of two s orbitals or two p orbitals is not called hybridization. However, orbitals of s type can mix with the orbitals of p type or of d type. Based on the type and number of orbitals, the hybridization can be classified in various subtypes such as SP3, SP2, SP, SP3D, SP3D2, etc. It must be remembered that only the orbitals of nearer energy values can participate in hybridization. Now, the different types of hybridization. Hybridization can be classified in various subtypes such as SP, SP2, SP3, SP3D, SP3D2, etc. First of all, let us discuss SP hybridization. Intermixing of one s and one p orbitals of almost equal energy to give two identical and degenerate hybrid orbitals is called SP hybridization. These SP hybrid orbitals are arranged linearly by making 180° of angle. They possess 50% S and 50% P character. SP hybridization can be exemplified by taking into consideration the structure of beryllium chloride BeCl2. The electronic configuration of beryllium in ground state is 1s2 2s2. Since there are no unpaired electrons, it undergoes excitation by promoting one of its 2s electrons into empty 2p orbital. Thus, in the excited state, the electronic configuration of beryllium is 1s2 2s1 2p1. If the beryllium atom forms bonds using these pure orbitals, the molecule might be angular. However, the observed shape of beryllium chloride is linear. To account for this, following SP hybridization was proposed. In the excited state, the beryllium atom undergoes SP hybridization by mixing a 2s and a 2p orbital. Thus, two half-filled SP hybrid orbitals are formed which are arranged linearly. These half-filled SP orbitals form two sigma bonds with two chlorine atoms. Thus, beryllium chloride is linear in shape with the bond angle of 180°. Similarly, there is another molecule called acetylene which is also SP hybridized at its carbon atoms, having a bond angle of 180° between hydrogen, carbon, carbon and hydrogen. Another type of hybridization is SP2 hybridization. Intermixing of 1s and 2p orbitals of almost equal energy to give three identical and degenerate hybrid orbitals is known as SP2 hybridization. The three SP2 hybrid orbitals are oriented in trigonal planar symmetry at angles of 120 to each other. The SP2 hybrid orbitals have 33.3% S character and 66.6% P character. SP2 hybridization can be exemplified by taking the example of boron trichloride BCl3. The electronic configuration of boron in ground state is 1s2, 2s2, 2p1 with only one unpaired electron. Since the formation of three bonds with chlorine atoms requires three unpaired electrons, there is promotion of one of 2s electrons into the 2p sublevel by absorbing energy. Thus, boron atom gets electronic configuration 1s2, 2s2, 2px1, 2py1. However, to account for the trigonal planar shape of this BCl3 molecule, SP2 hybridization before bond formation was put forward. In the excited state, boron undergoes SP2 hybridization by using a 2s and 2p orbitals to give three half-filled SP2 hybrid orbitals which are oriented in trigonal planar symmetry. Boron forms three sigma sp-p bonds with three chlorine atoms by using its half-filled sp2 hybrid orbitals. Each chlorine atom uses its half-filled p orbital for the sigma bond formation. Thus, the shape of boron trichloride is trigonal planar with bond angles equal to 120 degree. Similarly, ethylene, that is CH2 molecule, shows sp2 hybridization at both carbons, and the bond angle over here also is 120 degree. Now, the third type of hybridization is SP3 hybridization. In this case, 1s and 3p orbitals of almost equal energy intermix to give four identical and degenerate hybrid orbitals. These four sp3 hybrid orbitals are oriented in tetrahedral symmetry with 109 degree 28 minutes angle with each other. The sp3 hybrid orbitals have 25% s character and 75% p character. Methane, ammonia and water all show sp3 hybridization with tetrahedral, trigonal, pyramidal and bent shapes respectively. Another type of hybridization is SP3D hybridization. In this case, 1s, 3p and 1d orbitals of almost equal energy intermix to give 5 identical and degenerate hybrid orbitals, which are arranged in trigonal bipyramidal symmetry. Among them, 3 are arranged in trigonal plane and the remaining 2 orbitals are present above and below the trigonal plane at right angles. The sp3 hybrid orbitals have 20% s, 60% p and 20% d character. The best example that can be taken for this type of hybridization is that of phosphorus pentachloride PCl5. The ground state electronic configuration of phosphorus atom is 1s2, 2s2, 2p6, 3s2, 3px1, 3py1 and 3pz1. The formation of phosphorus pentachloride PCl5 molecule requires 5 unpaired electrons. Hence, the phosphorus atom undergoes excitation to promote one electron from 3s orbital to one of empty 3d orbitals. Thus, the electronic configuration of phosphorus in the excited state is 1s2, 2s2, 2p6, 3s2, 3px1, 3py1, 3pz1 and 3d1. In the excited state, intermixing of one 3s, 3 3p and one 3d orbitals takes place to give 5 half-filled sp3 hybrid orbitals, which are arranged in trigonal bipyramidal symmetry. That is, 3 orbitals are arranged in trigonal planar symmetry, whereas the remaining 2 are arranged perpendicularly above and below this plane. By using these half-filled sp3 hybrid orbitals, phosphorus forms 5 sigma sp3p bonds with chlorine atoms. Each chlorine atom makes use of half-filled 3pz orbitals for the bond formation. The shape of phosphorus pentachloride molecule is trigonal bipyramidal with 120 and 90 of chlorine phosphorus chlorine bond angles. Another type of hybridization is SP3D2 hybridization. In this case, intermixing of 1s, 3p and 2d orbitals of almost same energy by giving 6 identical and degenerate hybrid orbitals takes place. These 6 sp3d2 orbitals are arranged in octahedral symmetry by making 90-degree angles to each other. The arrangement can be visualized as 4 orbitals arranged in a square plane and the remaining 2 are oriented above and below this plane perpendicularly. Another type of hybridization is SP3D3 hybridization. In SP3D3 hybridization, 1s, 3p and 3d orbitals of almost same energy intermix to give 7 SP3D3 hybrid orbitals, which are oriented in pentagonal bipyramidal symmetry. 5 among the SP3D3 orbitals are arranged in a pentagonal plane by making 72 degrees of angle. The remaining are arranged perpendicularly above and below this pentagonal plane. Now, let us discuss the concept of resonance in covalent molecules. Sometimes it is not possible to represent the molecule or ion with only one structure. More than one structures have to be proposed for such molecules. But none of these structures exactly explains all the observed properties of the molecule. The solution is to write a weighted average of all the valid structures which explains all the properties. The condition is usually referred to as resonance or mesomerism or delocalization. The representation of structure of a molecule as a weighted average of two or more hypothetical structures which only differ in the arrangement of electrons but with the same position for atoms is referred to as resonance. There are various salient features of resonance, which are: the hypothetical structures with different arrangement of electrons but with identical position of atoms are called resonance structures or canonical forms or contributing structures. The resonance structures are only imaginary and the actual structure of the molecule is considered as the hybrid of all the valid resonance structures. Now, what is a resonance hybrid? The weighted average of contributing structures is known as a resonance hybrid. It is considered as the actual structure. The energy of resonating hybrid is always less than the energy of any of the contributing resonance structures. The resonance structures are formed only on paper due to delocalization of electrons and not by changing the position of atoms. The delocalization of electrons is shown using curved arrows. One should keep in mind that the individual resonance structures do not exist and the molecules do not resonate. They do not switch back and forth between these structures. The actual molecule is simply the hybrid of all these imaginary resonance structures. Hence, the delocalization of electrons is also an imaginary process which helps in understanding the process of resonance. We can take various examples of resonance, in which we can take the example of ozone, we can take the example of carbon dioxide, we can also take the example of benzene. We can have two contributing resonance structures in ozone molecule. However, we can have only a weighted average of the two as the actual structure of the ozone molecule. Similarly, in case of carbon dioxide, we can have various contributing structures, but the actual resonance hybrid represents carbon dioxide molecule as a pure and true structure. Similarly, in case of benzene, we can have 5 contributing structures, out of which 2 are called the Kekule structures and other 3 are called as Dewar structures. Neither of the Kekule or Dewar structures is the actual structure of benzene molecule. However, the actual structure is a resonance hybrid of all these structures. That's all we have for you in the present lecture. Thanks, dear friends.